Hello, everybody. Welcome to this first presentation of Geocron January 2023. My name is Gloria Lopez, and I will be introducing you to the world of luminescence dating field sampling strategies. I would like to start by thanking the IGCP 725 organizers for this awesome virtual workshop, and I hope that you like what you're going to get yourselves into. As we have split the different dating methods among different experts, make sure to check the second presentation by my esteemed colleague Sébastien Huot that is going to explain you everything about the principles, measurement techniques, and H calculation for luminescence dating. I will be concentrated in the topics that you see on your screen right now, mostly because they're pertain to, or they're very important to, the sampling strategies. So I would be quick on the basic principles and concepts, on the fundamentals of the luminescence cycle and dosimetry, tell you about why is it important to understand sunlight exposure, and get into the field techniques themselves, where and what to sample, what materials are you sampling, what are the minimum required tools, how to sample an OSL sample, and give you some insight about an awesome little tool called the Portable OSL Reader, give you some words of caution, and quickly introduce you to lab sample preparation. And I will be ending by giving you some useful and key references that have been published lately, or some oldies that are very good to know. So let's start by asking, why is luminescence dating important? Well, basically because of two things: its wide age range and its variety of materials. Basically, you can date anything from clays to gravel, wherever you have quartz or feldspar, or both. So you can date pretty much every single sedimentary environment on the surface of the planet, but also rock surfaces and man-made materials. So that makes it a pretty important dating method, not only because the main minerals that it dates is quartz and feldspar, basically potassium feldspar, but also because it has a large variety of applications, as you can see here, like so far about 13, 14 of them, which covers almost everything that you can think of, but also because it can also date minerals such as zircon, calcite, and there's been experiments in apatite. So these three are in brackets because they're not very commonly dated, and it's actually quite complex to measure them. So we don't use them as commonly. The ones that we use commonly and for service, for commercial services, for example, are quartz and feldspar, undoubtedly. As you may or may not know, luminescence dates the last time the sediment saw sunlight. So basically it dates directly the landscape features or events and the depositional age of the sediment. So it can date pretty much everything that you see here in this figure, which Sébastien is also going to show you a couple of times. So basically, the furthest you go from the source of the sediment, which is the mountains, for example, the better the grain gets in order to get datable. So everything that is on the coastal zone is actually better to date than anything else because it's further away from the source. It has undergone more transport and reworking. It has undergone more cycles of exposure in terms of exposure to the sunlight. So it has a better signal sensitivity. And this is something extremely important in order to get a more accurate age. For those of you that do not know how luminescence works, this is a very simple, quick intro of the basic principle. So you have a bunch of radioactivity that is happening in your surrounding environment, and you have all these minerals, quartz and feldspar, little minerals, crystals, actually, that have holes in their crystalline structure. And those holes trap electrons produced by radioactivity. And then when you have sunlight exposure, all these electrons are going to get out of those traps in the form of luminescence, of light. Then when it gets buried again, then all these traps get refilled by those electrons produced by ionizing radiation. So it's basically the principle works on energy absorption and release during burial and during stimulation. That is why it's also called the trap charge dating method, and it applies to both optically stimulated luminescence and thermoluminescence, which stimulant is actually heat, not the sunlight. And how does this happen? Well, this is some pretty cool physics at the atomic and molecular level, but I'm not going to get into that because it's actually quite complicated. I'm just going to very simply tell you that it is changes in the different states that involve these transitions of electrons when they're trapped during the equilibrium stage, and when they get stimulated, they get into a different metastable state that actually releases the OSL or TL signal. So it releases the electrons in the form of luminescence, and that's what we measure. One fundamental thing to understand is that luminescence undergoes cycles, and these cycles depend on the geological and anthropogenic processes at work. So a little grain of sand can trap energy, electrons, and detrap them, so release them in the form of luminescence, several times. It can go on and on and on for seconds, hundreds of years, thousands of years, all depending on how many times it gets eroded, transported, and deposited or redeposited. So this is a recycling of cycles until you collect the sample. This is a little animation of the previous graph, so it's easier to visualize. So you have the level of luminescence in the mineral grains before the erosion happens. Then the erosion happens, you have sunlight exposure, you have bleaching of the luminescence signal. Subsequently, you have the rebuild of the luminescence signal if your grain gets buried again or heated again, and until you get your sample collected. So that is your luminescence stage. In the laboratory, we're going to measure that signal, so the loss of that signal due to stimulation. But this, Sebastian is going to cover in much more detail. So in the lab, so you know, like this is the reader in which we measure the luminescence signal, and it actually has a turntable in which you put your little samples on these very small discs, and you measure them either individually or grain by grain. Is it also possible? Another fundamental aspect to take into account, which is crucial for sampling, is dosimetry. So all the radioactivity that happens inside that sediment is going to have an influence in your sample. That radioactivity is in the form of decaying of uranium, thorium, and potassium isotopes. So it's very important to actually understand your lithology and the stratigraphy of your sampling area. The geometry of the deposit is also crucial because we're going to see later on that it influences which areas are better in terms of bleaching or effective bleaching and which areas are worse. Erosion, reworking, transfer, and deposition processes are also key to understand because they're also going to have an effect in your dosimetry. And obviously, whether or not in the sediment you have quartz or feldspar is key, because if you don't have these minerals, obviously you won't be able to date. So in your sediment, you're going to have the influence of alpha, beta, and gamma rays at different depths or at different distances. So the alpha rays only influence 20 to 30 microns in distance, beta 2 to 3 millimeters, and gamma 30 centimeters. This is the reason why we have to be extremely careful when selecting the sampling spot, because everything around 30 centimeters should be homogeneous enough in order to have an homogeneous dosimetry, such as here, for example. I'm taking the sample in the middle of the unit, away from these other two different layers. And I selected this layer and not this one because then my 30 centimeters are going to be around or inside homogeneous lithology, not here, for example, which is going to be influenced by this other unit. So selecting your sampling position is going to be crucial in luminescence. That's why dosimetry is so important to understand, and by so it's very important to understand your lithology. So you can see here where it's bad or poor to take a sample because of the influence of surrounding lithology. Another concept to understand is effective bleaching, which translates into how turbulent the flow that transports your little grains of quartz and feldspar is. So it's very different if the flow is clear as opposed to a very turbulent flow such as this bore. So think about a tsunami wave versus a normal steady marine atmospheric conditions wave. So the clearer the waters, or the clearer the flow in which your grains are getting transported, the more sunlight gets penetrated, so the better bleached your grains are going to be. And this is extremely important to understand for every single deposit or unit that you're going to sample. And understand the process itself, because sometimes only the grains at the very surface of that flow, which means at the very surface of that deposit, are going to be the best bleached, than as opposed to those in the center of the deposit or at the back of the deposit. This is true for any type of deposits, like landslides, marine deposits, lagoon deposits, estuaries, lakes, etc. So always think about how clear was the flow before you sample anything. For example, I have here two little videos that I'm going to run really quickly by you. So one is about a little river flowing into a beach in Alaska, somewhere in Alaska. I can't remember where exactly, but you can see that the water is extremely clear here on the left-hand side. And all these grains that are moving by traction, suspension, and rolling are being effectively bleached because of not only the depth, the water thickness, but also the sunlight exposure. Here on the right, you have a desert dune. This is somewhere in the Moroccan Sahara. And you can see that all the little grains that are at the very top of the dune, at the very surface of the dune, are being completely exposed to sunlight. And this is actually one of the best examples of effective bleaching that exists in the sedimentary environment. So everything that gets blown by the wind is actually very good to sample. And I put a photo of my feet in 1 meter depth water. And you can see that the sun is getting into all this sediment down below here. So all these ripples, all these little grains of quartz are being effectively bleached. So every time that you think about sampling for OSL, think like a grain. Where would I be to be the best bleached possible? And which part of the deposit is better for me to take a sample from, because not all parts of the deposit might have been correctly bleached during the formation process. Why am I telling you all this? Well, it all gets summarized in this slide. Basically, when you sample something that has been very well bleached, such as an aeolian environment, a beach, a dune, or a desert, well, you get this. Like all your little grains were exposed at the same time homogeneously during your transfer and deposition process, which means that all of them are going to have the same luminescence signal, which translates into the same age. So this is very straightforward to calculate and very accurate to do. As opposed to this other sample that comes from an incomplete bleeding environment, so a turbulent flow, a turbid waters, for example. So you're going to have a multitude of different signals being accumulated here, which translate into different ages. So this is actually very common in glacial or fluvial, alluvial, and colluvial deposits. And it's actually quite complex to calculate an age here because your sample is going to be very skewed in terms of luminescence signal. And you're going to have a multimodality of luminescence signals that you have to pick the most accurate from in order to calculate an age. But all this, Sebastian is going to explain them to you in the next presentation. Where and what to sample, finally? Well, it all comes down to these 10 factors that are key things to understand of your deposit, of your target sample, and just make the questions. Like, for example, was the deposit well exposed to sunlight? Did the event or the process happen during the daytime? Because otherwise, you cannot date it with OSL. Do I have quartz and feldspar present? For real, you have to check the mineralogy. Is there potential for preservation? Like, is there enough space in the area to create layers that are thick enough for me to sample? If I were a little grain of sand, how eroded, how well transported, how well deposited was I? What's the extent of the deposit? So you have to understand which areas are better or worse in terms of effective bleaching within the same deposit. How far am I, in terms of if I were a grain of sand, how far am I from the source? What's the thickness of the unit in order to choose correctly the sampling vessel, the diameter of the sampling vessel? If the sampling point, is it too far away from where you are? Like, for example, if the outcrop is extremely high, or if what you want to sample is on the subsurface, what type of equipment should I use? Are there any kind of reworking processes, syn or post-depositional stresses happening in the deposit? Are there ants? Are there wasps making little burrows? All these little things you have to take into account, and you have to know them before getting into the field for sampling, because this is going to save you much time and headaches after you sample it. So what equipment should I use? Well, this is actually a collection of the basic sampling equipment you should have in order to get an OSL sample. I always say that the more the merrier, but not everybody can afford it. Or, I mean, you don't have the time to collect all this. So the basic equipment is in this little figure, and this is only for simple sampling. And it consists of a black or opaque PVC or metal tube with something in the end that you can hammer it into. Then you have a shovel, you have a rubber mallet, your cell phone or a photographic camera. You want to have some duct tape, some black bags and transparent bags, your notebook, measuring tape, a GPS because the location is extremely important, and this, not everybody has a portable gamma spectrometer, but this is actually something very good and nice to have if you can have in situ measurements. There are various ways to sample for OSL, but the most basic and simple one, and the one used in the majority of labs or by the majority of non-experts, is the tube inserted inside your target unit, as shown in here. So it's a horizontal tube that you're going to hammer or push into the unit. Always, 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 besides that tube, please do take a sample for the symmetry, which means take as homogeneously as you can material from around the 30 centimeters around the sampling point, and also get a little bit from inside that hole too. So you can use this as your material for your annual dose rate whenever you don't have a portable gamma spectrometer with you to take the measurement in situ. Something really important to remember is that the diameter of your horizontal tube is going to be dependent on the unit. For example, it's very different to sample something that is 40 centimeters thick, such as this heavy mineral unit, as opposed to these extremely small 1 to 5 centimeter heavy mineral layers. So here you need something that is actually half the size of your layer, as opposed to this little tube here. So always have that in mind. For example, a curious anecdote. During my PhD, I needed to sample these hurricane opal layers, but I didn't have a PVC pipe small enough to sample these. So I actually used this casing, or a similar casing, painted it black, cut it in the middle, and made micro tubes out of it in order to sample these. So always remember to understand what you're going to sample, know that it takes time to sample and effort, because it's very different to, let's say, for example, that you have a semi-exposed outcrop. Sometimes you have to clean it very well in order to take the sample, and sometimes you need to dig a trench in order to make a clean outcrop. in order to take the sample. So sampling is not easy. Sampling takes a lot of effort and a lot of skill, and you have to give it time because sometimes a sample can take up to 2 hours to collect. Also bear in mind that sometimes you won't be able to take an OSL sample directly from your deposit. So think about other units that could be dated or soils or things like that. So always have a backup plan in case your OSL doesn't work or in case you want to couple your OSL age with another type of method. In terms of other ways of sampling, there's drilling that you can also take horizontal samples with in exposed outcrops. The problem here is that I highly recommend an expert to do this for you because this requires a lot of knowledge in terms of how to use the drill bit and not let the heat from the drilling bleach your samples. There are special circumstances where your sediment is extremely compacted that no drill gets in. So you're going to have to do blocks, to carve out blocks, such as these ones that I'm showing you here, in order to get an OSL sample. So these blocks are more complex to process in the lab, but are the solution when you have very compacted materials. Also, sometimes when you're drilling out the sample, it cannot be exposed to daylight. So you always have to have a tarp with you in order to avoid light shining into your sample because you're collecting the sample in an exposed matter. You're not encasing it in a vessel such as your little PVC or a metallic tube. Last but not least, in terms of exposed outcrops, there's night sampling too. This is quite difficult, dangerous, highly complex because not everybody sees at night, let alone with your special red flashlight. So again, expert hands and guidance for this one because I won't recommend non-experts to do this, but it exists and we've done it. OSL samples can also be taken from sedimentary cores. However, even though it's very convenient, very few experts actually accept dealing with these long continuous cores because the OSL samples are going to be very small. Bear in mind that you have to split open the core and have enough material in order to process in the lab to get at least a minimum of around 2 grams of purified quartz or feldspar grains. So your sediment has to be really quite quartz or feldspar rich in order for you to get from a slab of around 2 centimeters long, more or less, to get enough grains, purified grains, for the measurement. So this is why this is extremely complicated and you have to be cautious about it. Same goes for any machine operated augers or for any equipment that uses liners. Liners are actually have a small diameter than the PVC or metallic pipes that I showed you previously. So these guys need to be painted black. And here, if you split open one of these, you're going to have actually less sediment than the previous continuous cores that I showed you. In this case, you're going to have to cut a little section out of these liners in order to get enough material to get suitable grains to date. So again, this requires expert hands and guidance. Finally, you can also use a soil test auger or a hand gouge in order to get your sample. So this is actually quite nice in order to test for the type of material that you will be sampling and get to know if you have quartz or feldspar in your sample. And with that in mind, here comes the portable OSL reader, a very useful little tool that helps you detect in the bulk sample without being processed if there's OSL signal at all, if you have quartz or feldspar. it can be used for several stratigraphic things. You can actually check if there's erosion reworking happening, and it's something very, very useful that not all labs have. It's something quite recent, let's say, but extremely practical to have. Once you have all your samples ready to be shipped, make sure you have all the information required by your OSL expert or your OSL lab, because there's a lot of little details that we need to know in order to correctly calculate the age. So many labs now have a sample submittal form that details everything that we need to know for a proper OSL calculation. Make sure to do this, fill it out in the field, not once you finish your field work, because there's a lot of detail here that is crucial for us. So make sure you do it correctly and always ask your OSL person. Also, one other thing is that make sure to always carefully manipulate and store your samples during field work and during transportation to the lab, and just take good care of them, because scorching heats or really freezing cold weather can damage your OSL sample, can bleach it. I've had several cases of this during my professional life, and you can only see this at the end after processing all the sample, after measuring, because all the measurements come to zero. So, and the person didn't know. So make sure you treat your samples well in order to avoid any future problems. In terms of sample preparation, obviously everything has to happen in a dark room, such as this one. Turnaround times can be a little longer depending on the type of material. So usually you have between 2 to 3 weeks, up to 2 months, depending on how compacted the sample is and the grain size of selection. Why does it take so long, you might say? Well, because we have around 10 steps to go through during this physical-chemical treatment in order to get purified mineral grains. Remember, 2 grams needed from a little tube or your split open core, and also POX or enough material in order to run dosimetric analysis from the bulk sample that you take for dosimetry. I covered now all the field strategies and everything else that Sebastian didn't cover in his talk, but I don't want to leave you guys before giving you some key references in terms of preparation, sampling, etc. So this one is actually the most recent article that both Sebastian and I participated in. This is freshly new out of the oven, a guide for interpreting and reporting luminescence dating results. The other 3 references are actually very good guides in terms of sampling and lab preparation issues and applications used in archaeology and paleoseismology, but very useful for any kind of geological coastal environment, sedimentary environment, etc. So please make sure to access them. Everything is available freely available in the internet or open access. With this, I thank you for your time and your interest in luminescence dating. And after this, I'm going to show you 3 slides with 3 textbooks that I consider key to have if you're interested in quaternary geochronology. Any questions at the breakout session, or you can actually also email me anytime you want. Thank you. Bye-bye. Book 1, Book 2, Book 3.